Boom, Julie and welcome. This is chapter 5, Chem 111. And today we are going to be discussing periodicity. Yeah, the almighty periodic table, okay? The periodic table itself is quite a long chapter. I don't know how many branches I'm going to divide this chapter into, but let's see what I can do within the short available space of time. The periodic table of elements. Now, this is simply the arrangement of all the elements you find in the world, all the chemical elements you find, the basic chemical elements you find in the world according to their increasing atomic numbers, okay? Demonstrated in the periodic table. Of course, this is in obedience to Moseley's modified periodic table. Now, before we go into the nitty-gritties of this periodic table, it is important that we study a brief history of what happened before the modern periodic table came into play. Now, many years ago, especially in the early 1800s, the first scientist that has ever attempted to organize all the existing elements in his time into a group of periods and into groups and periods is of the name Johann Wolfgang Duberiner. Johann Wolfgang Duberiner, and he made his attempt in 1829. In the course of trying to arrange these elements based on their properties, he arranged them in threes, making sure that the middle element has the mean atomic mass of the two other elements above and below. What do I mean? Lithium, sodium, potassium. Sodium in between. If you add the masses of lithium and potassium and divide by 2, it will give you sodium. So he was able to also get calcium, strontium, and barium. In fact, he had up to 4 sets of elements in that format, and then he named them the Duberiner triads. However, new elements were discovered later on in his time that could not fit into his 3-3-3 arrangement, and his own periodic table failed. Years later, a British chemist, the name of Newland, came on board. Now, with the idea of arranging elements according to their atomic masses and position them in 888. That means 8 elements in one period or one group, as the case may be, 8 elements, like that. And he likened them to the octave of music. Do, re, mi, fa, sol, la, si, do. So he likened them to the octave of music, probably because he was a musician anyway. And he named them, or he named the periodic table at that time, the Newland's octave periodic table. However, as time went by, new elements were being discovered that could not fit into his group of 888, and then at the end of the day, his periodic table also failed. And thereafter, the almighty Dmitry Ivanovich Mendeleev came on board. He is called the father of classification. And of course, he is the bedrock behind the periodic table we see today. He is the father of classification, not just because he brought something totally new into the periodic table, not just because he had a different approach. No, he was not the first person to attempt arranging elements in terms of atomic masses, nor the first to attempt arranging elements in terms of physical and chemical properties. No, he wasn't. Now, what actually made him very, very peculiar, that made him a genius, is his ability to hypothesize, to predict elements that are yet to be discovered. We are going to see that as we move forward. Now, as far as Duberiner, as far as Dmitry Ivanovich Mendeleev is, he is a Russian chemist who took his time and studied all the 63 elements that existed in his time. There were 63 in number. He studied each of their physical and their chemical properties and arranged them in periods and groups. At the end of his arrangement, he had a total of 7 periods and 8 groups, just like we have today. Now, and when he concluded his arrangement, he declared his Mendeleev periodic law, which states that elements in the periodic table are arranged as a function of their physical. Elements in the periodic table are arranged based on. No, let me take it this way. He said the physical and the chemical property of any element in the periodic table is a function of its atomic mass. He called it the Mendeleev law. The physical and the chemical property of any element in the periodic table is a function of its atomic mass. That means everything about the chemical property and the physical property is subject to the mass of that particular element. And he named it the Mendeleev periodic law. Now, this is where the genius part of Mendeleev came into play. His periodic table actually had some vacancies, about 3 vacancies. And into those 3 vacancies, he named the first vacancy as Aker boron, the next vacancy as Aker aluminium, the last vacancy as Aker silicon. Now, that means that word Aker simply means one after. After silicon, it was empty. After aluminium, it was empty. After boron, it was empty. And he said, a time will come, you guys are going to discover the elements that will fit into these empty boxes. I do not know their name, but I feel when the time will come, these elements will have so and so chemical properties. This element will be a liquid metal. This element will be a metalloid. This element will be this. And truly, years to come, elements were discovered that fit into his periodic law, his periodic table, so to say. And of course, Aker boron was later discovered to be scandium. Aker aluminium further discovered to be gallium, and then Aker silicon discovered to be germanium, which is a metalloid. Gallium is a liquid metal, just like he hypothesized. And this is what made him a genius. And this is what made him the father of classification, because he was not just able to predict what will happen in his time, he was also ready to hypothesize what will happen in years to come, of which it came to pass. Now, that does not mean that Mendeleev did not have flaws. Mendeleev had flaws. In fact, he has 3 solid flaws. The very first flaw he had was trying to arrange hydrogen in the periodic table. And this is the basic reason why hydrogen does not have a group nor a period in the periodic table. Hydrogen at times behave as a metal, behave as a non-metal, behave as a halogen. If it loses an electron, it becomes positively charged. Will you say it is a metal? If it gains an electron, it becomes negatively charged. Will you say it's a non-metal? If it gains an electron and becomes with 2 electrons in its first shell, will you call him a noble gas? So it became very difficult to group hydrogen in the periodic table. That was one challenge. Then the second challenge he had was with cobalt and nickel. If you check the periodic table vividly, cobalt and nickel, cobalt came before nickel. Meanwhile, cobalt is heavier than nickel. Cobalt has a mass of 58.9, while nickel has a molar mass or an atomic mass of 58.7. So courtesy demands that he would have just swapped them and have the case study. But he said no. Cobalt actually has some chemical properties and physical properties that makes him come before nickel. And of course, that one was also unanswered. And then the last one was manganese. Manganese was fit into the group of halogens, group 7 elements of the periodic table, of which till today, manganese still belongs to group 7, but however, in group 7b instead of group 7a. So if you check the whole periodic table we have today, turns around the works of Mendeleev. However, Moseley came into play. After studying all these drawbacks of Mendeleev, he came into play and changed one significant element in the Mendeleev periodic law. The Mendeleev periodic law states that the chemical and the physical property of any element in the periodic table is as a result of its basic function in mass. But he changed it to atomic number. He said the physical and the chemical property of any element in the periodic table is a function of its atomic number. That means the number is the basic determinant of the physical property and the chemical property of any element in the periodic table. And he did not take the glory to call himself Moseley's periodic table or Henry Moseley periodic table, as the case may be. Rather, he named it the modified periodic table, also called the modern periodic table. And that is what we use till today. Now, that takes us straight to the statistics of the periodic table. First, you must understand that the periodic table is made up of 7 periods and 18 groups, not 8 groups, 18, because you have 10 in the D blocks, okay? Good. Now, 8 periods, made up of 8 periods currently, instead of 7 periods, right? No, I think it's 7 period, not up to 8. 7 period. Rather, the 8th period is about to flush in. The reason being that we have a total of 118 elements in the periodic table. If we check the line of the 7th period, it's totally filled. So that means if any element is being discovered in the years to come, that element will give birth to a new period, which is period 8. Now, the next thing you need to know is that the vertical columns are called groups, also called the congeners, while the horizontal rows are called the periods. The groups are written in Roman numbers in terms of and letters A and B, and then from group 1A to group 8A, they are referred to as representative groups, while group 1B to group 8B, they are called the transition elements or the D block, as the case may be. Now, the inner transition elements are also called rare earth metals, right? They are the lanthanides and the anthonides, and the actinides in the periodic table, right? They are of two sets of 15 elements each in the periodic table at the bottom. Now, the periodic table has a total of 11 gases, all the noble gases excluding organosine, plus nitrogen, hydrogen, oxygen, fluorine, and chlorine. That makes it 11. And then it has 6 liquids. The 6 liquids, one of them is a non-metal, which is bromine, the only liquid non-metal, while the remaining are metallic liquids, which are mercury, calcium, rubidium, francium, gallium, right? So that makes them 5. And then the remaining ones are solids. But take note, you also have metalloids. And there are some elements in the periodic table whose state of matter are yet to be determined. Okay, they are yet to be determined. For example, organosine is not a gas, even though it is classified under the realm of noble gases. It is still not a gas. Its state of matter is not known because of its short life. There is what we call half-life. He has a very short half-life in milliseconds, right? Good. So bromine is the only liquid non-metal you have in the periodic table. There are 5 solid non-metals in the periodic table, very important, which are iodine, carbon, phosphorus, sulfur, and selenium, right? Iodine, carbon, phosphorus, sulfur, and selenium. And then you have 5 liquid metals, which we have named before. Mercury, the most common one, calcium, rubidium, francium, and gallium. In group 1 alone, you have the last 3 as the liquid metals. Then you have gallium, which is in group 3, if I'm not mistaken. And then you have mercury, which is already known from secondary school. It may interest you to hear that letter J does not have an element in the periodic table. No element in the periodic table is named J, right? All right. And then it's also important for you to know that hydrogen in the periodic table has no group, no period. We've said that before. All right, good. So if you go straight into the statistics proper, you will discover that out of 118 elements, 17 of them are non-metals. Out of the 17 of them that are non-metals, 11 of them are gases, 1 of them is liquid, and 5 of them are solids. Now, if you go straight into the metallic realm, you will discover that you have about 94 assumed metals, okay? 94 assumed, because there are some elements there that are artificially made, especially the last bottom in group 7. After the anthonides and lactonides, that's from 103 and above to 118, they are artificially made. So most of them, their state of matters are not known. So, but we can assume that they are under the concept, the group of metals, okay? So, however, from there down, you can assume 94, then 7 metalloids, okay? 7 metalloids, which we are going to see as this chapter unfolds itself. So that takes us straight away to hydrogen. We're going to start with hydrogen to study. Yeah, hydrogen, because hydrogen happens to be the first element in the periodic table, the only element without group, the only element without period, the only mysterious element in the periodic table, the Ogapata of them all, the lightest gas ever known that shall never be known. Hydrogen. So let's go into hydrogen. It is the simplest form of all the elements in the periodic table. It has no group, it has no period. It is found, or it forms compounds with almost all the elements in the periodic table except noble gases, right? Good. Preparation of hydrogen. Hydrogen can be prepared in 1, 2, 3, 4, 5, 6, 7 ways. 7 ways. The very first way of preparing hydrogen here is by the action of dilute concentrated, okay, not concentrated now, the action of dilute acid on metals above hydrogen in the electrochemical series. That is called displacement reaction, right? So assume zinc reacting with tetraoxosulfate 6 to give you zinc, tetraoxosulfate 6, and hydrogen being evolved. That's the best way to do that. Then a second way you can create or produce hydrogen in the laboratory is by the action of water or steam on group 1 element. Yes, by the time you pour water on group 1 element, hydrogen will definitely be evolved, thereby producing the hydroxide version of that metal. For example, potassium and water will give you potassium hydroxide and hydrogen. Okay, steam can only be applicable especially when they are very, very not too reactive, like lithium. Lithium is the least reactive in group 1. It may demand steam to be able to react. If you bring cold water, it may not react very well. Okay, good. So let's go to the next one. Is the action of steam on iron. Just pour steam, hot steam on iron. Hydrogen will be evolved, and the hydrogen produced here can be used to harden oil, margarine to be precise. So iron plus water in the form of gas will give you iron 4 oxide. That's iron 3O4 plus hydrogen. Then the next one there is by the electrolysis of water. That's another way to produce hydrogen. The electrolysis of water, water can just be splitted into OH minus and hydrogen ion. Then the hydrogen ion being produced combines with another hydrogen ion to give you hydrogen molecule. That's electrolysis. Then the next stage where to produce hydrogen is by the thermal cracking of hydrocarbons. Yes, thermal cracking of hydrocarbons can lead to the production of hydrogen. And then another way is by the dissociation of hydrogen molecule into its atomic form at a given temperature. Hydrogen can be splitted into hydrogen atoms, and usually it's an endothermic reaction. Endothermic in the sense that it will have to absorb heat from the environment to be able to achieve that. And then the last way you can produce hydrogen, as far as my record here is concerned, is by using the electric arc at a high temperature, or UV rays to produce atomic hydrogen used in welding metals. Perfect. So just remember them. Number 1, you can think of the electrochemical series. Number 2, just remember the action of water or steam on group 1 elements, the action of steam on iron, electrolysis method, thermal cracking method, dissociation of hydrogen, and then the use of electric arc. Stuff like that. Now, properties of hydrogen. Hydrogen happens to be the lightest of all gases, which we have said before. It is 1/4 the weight of air. That is the gospel truth. 1/4 that of air. And then it is colorless, odorless, and tasteless. It is moderately reactive and behaves as a group 1 element, as a group 7 element, and at times as a group 8 element, which we have explained before, reason why Mendeleev could not give it a position on the periodic table. It reacts with virtually all metals. It reacts with virtually all metals and forms alloys, stuff like that. So now that takes us to the binary hydrides. Binary hydrides. Hydrogen has the ability to combine with elements to form hydrides. Hydrides are a combination of elements, usually metallic elements. At times it can be non-metallic elements, but to form hydrides. For example, sodium hydride, potassium hydride, stuff like that. So combination of hydrogen with any other element to form hydrides. It can even be non-metals, like put hydrogen and nitrogen to form ammonia, stuff like that, hydrogen fluoride, stuff like that. So they are called hydrides. Now, there are basically 3 types of hydrides. We have the covalent hydride, we have the ionic hydride, and we have the metallic or interstitial hydrides. Now, what do we mean by covalent hydride? Covalent hydrides, from the word covalent bond, sharing of electrons, sharing, not transferring, covalent hydride. So it involves the sharing of electrons with elements it comes in contact with. And now there are 3 types of what? There are 3 types of covalent hydrides. You have the electron deficient, the electron rich, and the electron precise covalent hydrides. We start with the electron deficient covalent hydride. This type of covalent hydride is formed by hydrogen when it combines with elements in group 3 of the periodic table. For example, boron. Boron has only 3 electrons in the outermost shell, and by the time hydrogen gets in contact with them through covalent bonding, that's bond to each of the 3, you have 6 electrons. So it is actually deficient of an octet. and therefore that hydrogen bromide, I say hydrogen bromide, yeah, hydrogen bromide or boron hydride as the case may be, is not stable. It will have to react with another hydrogen boride or hydrogen bromide to form a diborane, which is called to form a dimer called diborane. Yeah, diborane, that's the name. So it is actually referred to as electron deficient because it is not up to an octet configuration. Now, the electron precise hydrides, these are formed when hydrogen combines with group 4 elements that have exactly 4 electrons in the outermost shell. And when this happens, each of these 4 electrons share electrons with hydrogen covalently, and at the end of the day you have exactly 8 electrons in the outermost shell, and so that makes it an octet configuration. That makes it a precise configuration, so they are called electron precise. Typical example is methane formation. Very important. Methane, carbon and hydrogen, methane. Okay, good. Now we go straight to the electron rich covalent hydride. Electron rich covalent hydride takes place when hydrogen combines with elements from group 5, group 6 and even group 7. When hydrogen combines with group 5 elements in the periodic table, remember group 5 elements in the periodic table have how many electrons in the outermost shell? 5 electrons in the outermost shell. So with one lone pair, that means 3 unpaired electrons. Those 3 unpaired electrons can take hydrogen with one lone pair remaining. The presence of the lone pair makes it an electron-rich covalent hydride. I hope you understand. Good. So a typical example of that is ammonia, taking nitrogen as an example with 3 hydrogen. If it is in group 6, you take oxygen as an example. It will have 2 lone pairs and 2 free electrons for covalent bonding, and that's water molecule. Another example of an electron-rich covalent hydride is fluorine, that will have 3 lone pairs and 1 free electron for covalent bonding, and that is hydrogen fluoride. Okay, now the law of octet configuration at times is being disobeyed by some elements in the periodic table, and these elements are hydrogen, lithium, beryllium. Hydrogen, lithium, beryllium. They disobey. Why? Because by the time they are completely bonded, they don't have up to 8 electrons in the outermost shell. That is the disobedience we're talking about. However, there are some other elements that are actually hypervalent in nature. In other words, they have more than the number of required electrons after bonding. Just think of an element that has a total of 5 electrons in the outermost shell, and each of these electrons get covalently bonded to. Let's assume that the lone pairs get destroyed. Phosphorus, for example, 5 electrons in the outermost shell, and each of them gets covalently bonded to. How many electrons do you think will be in that shell? 10, no longer 8. You see? So these guys have actually exceeded the octet configuration law. They are called hypervalence compounds. Sulfur is also another example. Sulfur has 6 electrons in its outermost shell, and when all 6 electrons are occupied, at the end of the day, sulfur will have a total of 12. So that's a disobedience to the octet configuration. So we are done with the first part of the types of hydrides, which is a covalent hydride. So now we are entering the ionic hydride. From the word ionic, transfer of electrons from one element to another. Okay, sodium transferring his last electron to hydrogen to form sodium hydride is an ionic hydride. You know, magnesium transferring 2 electrons to 2 different hydrogen to form magnesium hydride is an ionic hydride. Now the beautiful thing about this hydride is that they actually are very good conductors when they are liquid in form, but by the time they are solid, they behave as non-conductors. That's the gospel truth, just like sodium chloride. When it is solid, it doesn't conduct, but by the time water gets in contact with them, they become very good conductors. So they are called saline hydrides, for that matter, saline hydrides. So that takes us to the metallic hydride range. Metallic hydride. According to metallic hydrides, these are hydrides that are actually formed when hydrogen come in contact with transition elements. Oh yes, you heard me well. When hydrogen come in contact with transition elements, that is D block elements and even F block elements, they form what we call metallic hydrides or interstitial hydrides. And the gospel truth about their hydrides is that they have variable oxidation state. We know that transition elements naturally do have variable oxidation states, so their oxidation states are not stable. So their formulas are not also stable. So you hear things like titanium hydride, palladium hydride, zirconium hydride, and tomorrow you see different values for them. However, it is important for you to note that elements of group 1b, group 2b, group 3b, group 4, and group 5b are ready to react with hydrogen to form interstitial hydrides. That is group 1b to group 5b. Now, by the time we enter group 6b, only one element is ready to combine with hydrogen to form an interstitial hydride, and that element is chromium. By the time you enter group 7 and group 8, none of them will react with hydrogen to form a metallic hydride. None. So you have to remember this very well, because these are key facts that will definitely help you as far as preparation is concerned. So metallic hydrides here actually have similar properties with their parent elements. When they mean parent element is that if maybe we take zirconium to react with hydrogen to form zirconium hydride, zirconium is the parent element, right? So zirconium hydride now have similar properties with zirconium, right? That's what we mean. So metallic hydrides here have similar properties with their parent elements, but are not as effective as the parent element itself. For example, as far as heat conduction is concerned and electricity is concerned, zirconium hydride is better than zirconium is better than zirconium hydride. That's what we're trying to say. All right, so that takes us to isotopes of hydrogen. Very important. So we're going to discuss isotopes of hydrogen, isotopic effect, and then hydrogen economy, so that we can call this part a day. So isotopes of hydrogen. Naturally, hydrogen has 3 isotopes, which are the proton, the deuterium, and the tritium. The proton has no neutron, but 1 proton. Deuterium has 1 proton and 1 neutron, while tritium has 1 proton and 2 neutrons, right? Good. It is important for you to know that protium is the most abundant of all these 3 states of hydrogen. The most abundant. It is about 7,000 times more available than deuterium. And deuterium is about 0.7 times 10 to the minus 14 times more available than tritium. Tritium, however, is the one that is the most rare among the 3 of them, and happens to be radioactive. Very important. Take note, protium water is H2O, the normal H2O, you know. Deuterium water is D2O, which is also called heavy water. Tritium water is called super heavy water, and that is T2O. Now, it is radioactive. Why do you call deuterium oxide heavy water? It is tagged heavy because of the extra neutron that contributes to about 10% by weight compared to the ordinary water. So it's called heavy water because it is 10% heavier than the natural water, and the 10% heaviness comes as a result of the extra neutron in deuterium. Okay, very, very important. But take note, deuterium oxide, which is deuterium water, is not very good for health. The reason being that it does not easily dissolve. The intermolecular force of attraction existing between the hydrogen and oxygen are very strong, and on that note, they cannot easily be broken down into your system, and because they are not easily broken down into your system, they will remain in your tummy and at times can lead to death. Very important. And then in some cases, they don't even initiate metabolic activity within your body, so they become very toxic. As far as tritium water is concerned, don't try it because you will surely die because it is radioactive. It will emit beta particle in you that can lead to cancer and eventually death. Now, the toxicity in deuterium water compared to the ordinary water brings about what we call kinetic isotopic effect. Very, very important. So isotopic effect is caused by the difference in the mass between the 2 isotopes of hydrogen in chemical reaction. You have a reaction of water dissociating into hydrogen and OH minus, and then you have a constant of 1 times 10 raised to the power minus 14. Now you have deuterium water dissociating into D plus and OD minus, and you have a constant of 0.2 times 10 raised to the power minus 14. So this difference in constant is very significant, and it is what is responsible for what we call isotopic effect. And it's important for you to know that isotopic effect decreases in magnitude as the atom becomes bigger. That invariably means that the bigger the atom, the smaller the isotopic effect in its isotopes. You get it? The smaller the atom, the bigger the isotopic effect in its isotopes. That's what we are trying to say. So isotopic effect is inversely proportional to the size of the atom. And that takes us to hydrogen economy. What is hydrogen economy? Hydrogen economy is just the procedures involved on how to harness hydrogen and store in cylinder. That's hydrogen economy. And the best way to harness hydrogen in that today's world is through solar energy, okay? And that is always done by the use of a catalyst. And the best catalyst used in trying to get hydrogen from the sun is ruthenium, that bunkum ruthenium that disobeys both Hofburg and Hund's rule of multiplicity. Not really in terms of, disobeys both laws. Crazy. That's ruthenium 44. That's the atomic number 44. Now, what ruthenium does is that as the rays of light comes in contact with this catalyst actually has a way of getting excited. And once it gets excited, is capable of reducing water molecules into hydrogen atoms, which are later on channeled into cylinders and stored under high pressure. And of course, there is also a need for an interstitial hydride inside the cylinder. And the essence of the interstitial hydride is to help retrieve the hydrogen from the cylinder by reducing the pressure. Interstitial hydrides are usually reversible in reaction. So that's basically what it is. So that is where we are going to stop for now so that the table won't be too long. So we have been able to look at the periodic table and hydrogen as the case may be. So in our next step, we are going to go into the various periods and groups. In fact, we are going to take them group by group from group 1 to group 8 and seal it up. Boom. Thank you.